Hello guys, welcome back to ptet.chemistry channel. So moving on from the previous video on chemical structure and bonding kind of topical MCQs, this is a question on aluminium chloride. If you have done electrophilic substitution mechanism, which you would have done in A2 of this Cambridge International Curriculum anyway, is to do with the benzene kind of chemistry. Benzene, which is just basically aromatic chemistry, okay, but this is how we can get the carbocation formation as the electrophile. You will learn more of this in organic chemistry eventually. So aluminium trichloride is that molecule. That should remind you of BF3, which is your case study. There is a 120 degree 3 bonding pair, 0 lone pair on the boron. Same deal here around the aluminium, 3 bond pair, 0 lone pair. You get 3 electron pair. That will give you the sp2 hybridization. Aluminium, that would tell you is trigonal planar, 120 degree. As the bond pair repel equally. Again, this is all part of the valence shell electron pair repulsion theory called VSEPR. But this question is saying that what makes this reaction possible? If you think about it, the AlCl3 has gone to AlCl4 minus. How does AlCl4 minus looks like? This is how AlCl3 looks like. This is pointing, it's coming out and putting it sideways. So this is pointing out from the screen towards you. This is going into the screen away from you. This is in the plane of the screen. Is sp2 hybridized because on the aluminium there is a 3p orbital which is unhybridized. And we know the 3p orbital is dumbbell in shape, so that is empty. Because that is empty, you can have a chloride with a lone pair occupying it in such a way that you get a dative covalent bond from a chloride ion. Now you are no longer trigonal pyramidal. Now you are no longer trigonal planar, because now you are tetrahedral with 4 bond pair, including this dative covalent bond, which give you aluminium negative charge because it's a chloride bringing the lone pair of electrons, donating both the electrons in the covalent bonds to aluminium. That is the very definition of a dative covalent bond, which you have covered in your classroom or from your own reading. Yeah, so that has become tetrahedral aluminium. Oops, I don't want that. I don't want that either. I don't know why that. Anyway, so that has become aluminium tetrahedral carbon sp3. Not carbon sp3, tetrahedral aluminium sp3 hybrid. Okay, so it's gone from 120 degree to 109 degree there. All right, it's all down to the empty orbital that was unhybridized. So it's not the chlorine atom that has the vacant p orbital. It's the aluminium atom with an incomplete octet of electrons, only 6. So it's got 1 times empty orbital. Okay, and it's got nothing to do with the fact that it's covalent, or it's got nothing to the fact that it can exist as a dimer in the vapor phase. Yeah, okay. So sometimes a lot of this multiple choice is all about, it might be a correct statement, okay, but it doesn't explain whatever you want it to explain, okay. So don't just go for the correct statement. Always look out for what makes it the best explanation of all. Yeah. Next question is asking you for 6 bonding electrons. So it's best if you draw out the whole thing. So C2H4 is a classic CnH2n, is an alkene. You have learned this in O-level. C2F6, it's just like C2H6, CnH2n plus 2. You would have learned this in O-level as well. Under alkane chemistry, Okay, except instead of hydrogen, the fluorine, just like any other group 17 element, they form single bonds in place of the hydrogen. So this is water, OH2 with single bond. And I'm just going to draw three-dimensional for the NF3. So you got a lone pair there, lone pair there. No lone pair on this carbon. So they use all their outer shell electron for bonding. Here above the carbon is sp2. Here above the carbon is sp3. That's 109 degree. That's 120 degree. If you're unsure where this come about, it's best you check out your textbook, or you can watch my video on A-level chemistry concept under chemical structure and bonding. There are concept videos on valence shell electron pair repulsion. I do not advise watching before you actually start reading your textbook first, yeah, okay. Contain only 6 bonding electrons. So these are bonding electrons, okay. So the electrons involved to form covalent bond, you have 1, 2, 3, 4, 5, 6. You have 6 covalent bond. Each covalent bond is 2 bonding electrons. That means 2 electrons that are involved in bonding. Bonding electrons are different from bonding pair of electrons, yeah. Earlier we talked about bond pair and lone pair. With bonding pair of electron, we only count the sigma. But don't forget that when you have a double bond, what you have also is you have a sigma and a pi. Okay, even though pi bond is not considered a bonding pair of electrons, okay, however, when you consider bonding electrons, pi bond is a covalent bond, therefore it's considered as bonding electrons. So I also count 1, 2, 3, 4, 5, 6 covalent bond, 12 bonding electrons. I can cross that out straight away. There's also 6 covalent bond there. 1, 2, 3, 4, 5, 6, 7. I stand corrected. There is no 6 covalent bond there. There is 7 covalent bond there. So 1, 2, 3, 4, 5, 6, 7. Okay. So am I correct? 1, 2, 3, 4, 5, 6, 7. Whereas here is 1, 2, 3, 4, 5, 6. Yep. Okay. So there's 14 bonding electrons there. So do not jump to conclusion before you actually work it out. Yeah. So there are 2 covalent bonds. So there's 4 bonding electrons. 2 there, 2 there. Okay. So realistically speaking, you can tell here you have 3 covalent NF bonds. We are not counting the non-bonding electrons. We are just counting the one that are in the covalent bond. So there are 6 bonding electrons because each covalent bond is 2 electrons. All right. 3a part 8. This is basically asking you what is the shape? What is the shape of the molecule? All right. So you know OH2, that is water. Okay. Oxygen is in group 16. So 6 valence electrons. So 2 bond pair, 2 lone pair. We talk about valence shell electron pair repulsion. So your lone pair, this is how you explain it, right? Will repel more than lone pair, bond pair. Will repel more than bond pair, bond pair. Realistically speaking, when you have 4 bonding pair, you started out with 109 degree. And then when you have only 1 lone pair and 3 bond pair, that's like ammonia. And now, because you have 2 lone pair, the lone pair repel a lot more than lone pair, bond pair. It push it down to 104.5 degree or 104 degree there. Okay, so some books will use 104.5 or 104 degree. That's the angle between the atom and atom. Okay, not between the lone pair and atom, but between the atom. How many lone pairs on the selenium? I know they ask on selenium. This is water. What is the difference? Well, you know, selenium is below sulfur. Here you have oxygen, sulfur, selenium, group 16. If there's something your O-level taught you, is that the element in the same group has the same number of outer shell electrons, they're going to have similar property. Okay, so you still have 2 lone pair on the selenium. Lone pairs, so 2 lone pair on the selenium. Okay. 3a part 9. So you got to identify structure and bonding. So magnesium oxide is a case study. Well, when I say case study, it's more like chemistry vocabulary, which you will have heard of from O-level. Magnesium oxide, we have giant ionic structure. This is a giant ionic lattice structure. Therefore, melting it, you need to break ionic bond. When you melt something that has a giant ionic structure, you need to break the strong ionic bonds between the cations and the anion. That is what you are breaking in order to melt a giant ionic lattice. Okay, you should know for each and every single lattice covered in A level, what do you need to break, and you justify your reasoning in your theory paper on structure and bonding by stating structure and then what do you need to break. Okay, here they say which solid exhibit more than one kind of chemical bonding. Okay, so brass is an alloy. So you did this back in O level or GCSE. It's an alloy of copper and zinc. So alloy is a mixture. So you still have giant metallic structure. If you have giant metallic structure, your bonding is going to be metallic bonding between the cations and the sea of delocalized valence electron. There's just one kind of bonding, metallic structure. Okay, copper is just metallic bonding because it also has giant metallic structure, where the bonding is just metallic bond between the sea of delocalized valence electron. That means the sea of delocalized outermost shell electrons and your cations. Okay, diamond is going to be your giant molecular structure. Again, another case study from O level, where it only has covalent carbon-carbon bond. Okay, so there's only one type of bonding there. Why does ice have more than one kind of bonding? D must be the answer because I've already crossed out the possibility there. Okay, so when you have ice, essentially ice is where you have a closely packed OH2 molecule, right? So the lone pair on the oxygen there are polar molecule like that. So what happened is they order up together. So the delta minus can get attracted to the delta plus of another water molecule, not just in the normal way, just like between water, but in a very ordered manner. Because when you think about the packing, okay, how are the water molecules being packed as a solid? Is that they are regularly packed in a giant lattice where they are arranged regularly in a regular pattern. Okay, but they are very close to each other, that compared to a liquid water, they are so close to each other that they rearrange themselves in such a way that your bond angle become 109 degree. And you know what give you the 109 degree instead of this also is 109 degree. So the oxygen become more like tetrahedral. And why is that? Whereas earlier we talked about just like water here, it's supposed to be 104.5 with 2 bond pair and 2 lone pair. But here, when you have ice, because they are so close together in the solid state, they can use the lone pair there to form very strong hydrogen bond due to the close distance. It looks tetrahedral because of the 109 degree from their crystal structure that enable us to get the bond angle and bond length, but it's more to do around each oxygen. Now you have like 4 bond pair. I put an inverted comma because 2 are actual covalent bond. The other 2 are hydrogen bond. They get so strong and so close together that they count as your bonding pair of electron. Because you use the lone pair on the oxygen to do that, you have no more lone pair, and then they look like tetrahedral 109 degree, like in your normal carbon bonded to 4 bonds kind of thing. So what we have here really is we have very strong hydrogen bond, but we also have covalent OH bond. So those are the 2 kind of chemical bond present in ice. In fact, not just ice, you also have hydrogen bond and covalent bond in between the water molecules, as well as between steam molecule. Is a bit difficult to say because gaseous molecules are so far apart that the hydrogen bond between them would have been broken in going from liquid water to gaseous steam. Alright, so that's the end of these reasonably short tutorials on these 5 questions involving chemical structure and bonding. So do subscribe to the channel if you find these videos helpful, and like the video if you find it helpful, really. I mean, and share with your network of friends, your colleagues, and even students if you are a teacher watching this. I hope it helps to explain some ideas, and let me know what else you want me to cover, and I'll think about it in future videos. Okay, see you in the next video. Thank you for watching.